Alright, in this video we're going to look at the product rule and the quotient rule. We've already talked about the sum rule and the difference rule, and now we're going to add to that. Now if you recall from previous instruction, the sum rule says that the derivative of a sum of two functions, the derivative of f of x plus g of x, is equal to the derivative of f of x plus the derivative of g of x. In other words, the derivative of a sum is the sum of the derivatives. So then you might guess that the product rule would be the derivative of a product equals the product of the derivatives. Let's test that. So we know that x cubed equals x squared times x. We also know that the derivative of x cubed equals 3x squared. So if this version, if what we're guessing to be true is true, then the derivative of x squared times x should also equal 3x squared. So let's try our theory out here. The derivative, we're saying we're questioning, we're not sure, so we're testing it. The derivative of x squared times the derivative of x. Well, the derivative of x squared, of course, is 2x times the derivative of x, which is 1, which is 2x. So they do not match. They do not match. So this is not true. And that's actually, this is the road that people who discovered calculus took right away. They tried that first and they discovered right away that it just doesn't work. So the product rule is not quite as simple as the sum rule. So we say that this does not work. So they quickly discovered that the product rule actually looks like this. If f and g are differentiable functions, then the derivative of f of x times g of x equals the first times, I always say the first times derivative of the second plus the second times the derivative of the first. Or we also could write that, just write it as f times s prime. F stands for first and s stands for second, plus the second times derivative of the first. That's what they discovered that the product rule actually turns out to be. So let's just try using that. First of all, we have to be able to recognize that the product rule is needed. And you can see in this function here in example 1, f of x equals x times square root of x. You have to see two separate functions, which would mean x occurs more than once. And I do have that. I have x, and then I have another x under the square root. So I have two separate functions. So my first function is x, and the second of the two functions multiplied together is square root of x. Okay. So using our product rule, since we now recognize that it's needed, it's the first times the derivative of the second plus the second times the derivative of the first. So we know the derivative of square root of x is 1 over 2 root x. And the derivative of x, of course, is 1. So this would be our derivative. Unsimplified. Okay. And so, I mean, it would be fine. Of course, it's unsimplified. In a simplified way, we wanted a simplified version so that we make sure we've got it on multiple choice, the x and the square root of x would cancel out, and we'd actually have, it would be square root of x over 2 plus square root of x, because this x and this x here and this square root would cancel in that way, and the square root would be on the top, which is just 3/2 square root of x. That would be a simplified version, because I have a half square root of x plus a full square root of x is 1/2 or 3/2 square root of x. So in a multiple choice test they might have that, 3/2 square root of x, and it certainly is simpler than the first one. Alright, let's try another example. So again, we can see that we have two functions. We have x twice multiplied together. Okay. So using my product rule, it's the first times the derivative of the second plus the second times the derivative of the first, which of course would be x squared e to the x, because the derivative of e to the x is e to the x, plus e to the x times 2x, the derivative of x squared. So that would be y prime. Again, that would be unsimplified. The simplified version, they are going to recognize that there's an e to the x in both terms, and we can factor that out. So again, this is the unsimplified, and this is simplified. Okay. All right. Last example of the product rule then. If f of x equals x cubed times g of x, with g of 3 equal to 2 and g prime of 3 equal to 6, find f prime of 3. Well, again, we have to differentiate this, and it is a product rule. X cubed is our first function, g to the x is our second function, g of x is our second function. So first times derivative of the second plus second times derivative of the first. So it would be x cubed times the derivative of g of x, okay, plus g of x times the derivative of x cubed. And of course this would be x cubed times g prime of x. That's the derivative of g of x, plus g of x times the derivative of x cubed is 3x squared. Now they ask us to find f prime of 3. This is f prime of x. Now to find f prime of 3, of course, we have to plug in 3. So it would be 3 cubed times g prime of 3. If I plug 3 in here and here and here and here as well, plus g of 3 times 3 times 3 squared. So this would be 27, and they gave us g prime of 3 to be 6. So that's multiplying. Plus g of 3, they told us, is 2, and again multiplying. 3 times 3 squared is again 27. So we have 27 times 6 plus 2 times 27, which is 27 times 8, which turns out to be 8 times 7 is 56, carry the 5, 8 times 2 is 16, 216. So that would be f prime of 3. Good. Alright, the quotient rule. Now again, just like we did with the product rule, we could look at the idea that of what we think the quotient rule might be, and again we would be wrong. Our guess, just like our guess with the product rule was wrong, our guess, if we guess similar to the sum rule, it would be wrong again. Okay, the quotient rule is again a little more complicated than that. So if these two are differentiable functions, okay, then the derivative of f of x divided by g of x equals g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. Looks a little complicated. I read it like this. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. That's the way I tell people to think of it. Alright. So if I want to take the derivative of this function, example 4 here, dy dx, it's a quotient, obviously a quotient. The quotient rule is easier to recognize because you obviously have to have two functions divided, usually going to be a fraction. So it would be the denominator, it's denominator times derivative of the numerator minus numerator times the derivative of the denominator all over the denominator squared. So in this case it would be x squared minus 2 times the derivative of x cubed minus 3x plus 2 minus the numerator x cubed minus 3x plus 2 times the derivative of the denominator x squared minus 2 all over the denominator squared. Let's fill in our derivatives here. It would be x squared minus 2 times the derivative of that is 3x squared minus 3 minus the x cubed minus 3x plus 2 times the derivative, that would be 2x all over x squared minus 2 squared. Again, this would now be an unsimplified version of the derivative. This would be the quotient rule. This would actually be y prime here without any simplification. And it would find you y prime, it'd find you values of the derivative just as well as any other version. But of course they're not going to leave it that way. They're going to distribute, they're going to FOIL, they're going to simplify things. So if I'm going to simplify this, they're going to distribute this 2x tool here, and they're going to FOIL here. And then they're going to combine like terms and make it a little bit simpler. So if I FOIL the first one, it will give me 3x to the 4th, okay, minus 3x squared minus 6x squared plus 6, and then minus, and I'm going to put all of this in parentheses because I have to distribute the 2x. So it would be 2x to the 4th minus 6x squared plus 4x all over x squared minus 2 squared. Now if I distribute this negative sign, the negative here, this would become plus, minus, these all would change signs in here. And now I don't need the parentheses anymore. So what I have is 3x to the 4th and negative 2x to the 4th. That makes 1x to the 4th. 3 minus 2 is 1. I have a negative 6x squared and a positive 6x squared, which would just cancel. And then I have this negative 3x squared left over, so that would be there. I have a negative 4x, nothing to combine it with, and a 6, nothing to combine that with as well, over x squared minus 2 squared. And you likely could leave it as the x squared minus 2 squared. It's unlikely that they'd FOIL that out because there's really nothing to combine it with even if you did. But this would be the simplified version of our derivative. Okay. All right. Let's do another one, another example. The equation of the line tangent to the curve g of x equals e to the x over x squared plus 2. So again, we're going to have to use the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So it would be x squared plus 2 times the derivative of e to the x minus e to the x times the derivative of x squared plus 2 all over x squared plus 2 squared. So if I fill in my derivatives, that's going to be x squared plus 2 times e to the x minus e to the x times x 2x all over x squared plus 2 squared. Now, in this case, I really don't care about actually finding the derivative. All I care about the tangent line, so I don't worry about simplification here. Okay, I don't worry about simplification. I just want to plug in, and because I need the equation of the line tangent, I need to have my y equals y1 plus m times x minus x1. And I already know my x1 and my y1 are this point here. So those are going to go in. Y equals, it would be e divided by 3 plus, I don't know my slope yet, and then x minus 1. Now I find my slope. This is how I find my slope when x equals 1. So I plug it in. 1 squared plus 2 times e to the 1 minus e to the 1 times 2 times 1 all over 1 squared plus 2 squared. So this would be 3, and that would be 2, and this would be 1 plus 2 is 3, squared is 9 on the bottom. So what I have is 3e minus 2e, which is e over 9. You know, without having a calculator or anything else to do, if I had this on a non-calculator, then I would just leave it as e over 9. Obviously with a calculator I would plug it in, but this would be e over 9 would be my slope, and there is the equation of the line tangent to that curve at that point.